So I have drawn a flash drum here with some liquid and vapor inside of the container and a feed. And that feed is going to be supplying the mixture into the container. So again, we don't know how much liquid or vapor we're going to have in this container, but we do know the temperature and the pressure. So that would be given to us. This temperature and pressure is actually going to relate to what we did in our previous video with the dew pressure and the bubble pressure. So if we were to look at our plot for those that we did in the last video, we are given the temperature, we have pressure on the y-axis, and then we have on our x-axis the mole fraction of the more volatile component, which can be x1, y1. And then we had our curves for bubble pressure and dew pressure. So that looked something like this. And if you remember, we had our dew pressure as the lower curve here and bubble pressure as the upper curve. And with our flash drum, we are actually going to be at a point between these two curves. So at some pressure that we are given, we can use this graph and information that we learned from before to calculate what our mole fractions are going to be. And this is because our mixture is separated between liquid and vapor phases. So we also have another component, which is going to be the total mole fraction of the more volatile component in the feed at the start. So we'll call that Z1. And if we were to have some total amount of feed coming into our container, so if our Z1, I'm sorry, not Z1, if our total amount coming in was 10 moles per second, then we can look at this on our plot, draw a little line down here, and see that at 10 moles per second, I did write that right, at 10 moles per second, we could say that the mole fraction of benzene is going to equal, so mole fraction of benzene of the feed at the start would be 0.4. But once that mixture enters our container, there is going to be a separation between the liquid and the vapor. It'll separate between those, and we don't know the composition of how that's going to react. So our x1 over here is going to be our mole fraction of benzene in the liquid phase, and then our y1 is going to be the mole fraction of the more volatile component benzene in the vapor phase. All right, so let's start coming up with some equations that we can use to come up with the Rashford-Rice equation. So here I have drawn a feed coming in to our container with some total mole fraction of the more volatile component, and then we have some separation into vapor and a liquid, which then is going to flow out into these tubes that I have drawn here. So we know our flow rate T is going to be equal to the sum of the moles in the vapor phase plus the moles in the liquid phase. Because our flow rate T is equal to the sum of the flow rate of the vapor flowing out and the liquid flowing out. So in our next video, when we do the binary mixture flash calculation, we're going to again be using benzene and toluene. So here what we can do is a mass balance with the more volatile component. And if you remember before, we used Z1 as the mole fraction of benzene in the feed. So we can represent the moles of benzene entering the feed as T multiplied by that mole fraction in the feed. So then we can do the same thing for our vapor and liquid phases. So we'll have vapor times our vapor fraction component plus liquid times our xi, which is in our liquid phase. So now if we were to talk about Raoult's law again, we can assume that it's valid here because we have an ideal mixture of two hydrocarbons. So again, as a refresher, Raoult's law is going to be the mole fraction in the liquid phase multiplied by the pure saturation pressure of a vapor. And that's going to be equal to our partial pressure, which is the mole fraction in the vapor phase times the total pressure. So one other thing that's going to be really helpful to us in trying to derive the Rashford-Rice equation is that we can represent the ratio of the mole fraction in the vapor phase to its mole fraction in the liquid phase as Ki. So that basically just looks like Yi divided by Xi. So one other thing that I forgot to mention about Ki is that if we're looking at our Rashford-Rice equation, or I'm sorry, if we're looking at our Raoult's law here, and we divide everything, both sides by xi, then we can solve for the ratio expressed by ki, so we would have yi over xi, and then we would get that our ki is equal to our pure saturation pressure over our total pressure. And this is going to be important because we know the temperature and the pressure, so we can use that temperature to find our pure saturation vapor pressure of each component, and we know pressure, our total pressure here, because that's given to us. So we can easily find the Ki value for both benzene and toluene. So now if we want to think about what our unknowns are going to be, so what we're trying to find in this situation here. So we want to know the amount of moles in our vapor phase. So that's just going to be our V. And we also want to know the amount of moles in our liquid phase. And we also want to know the composition of our mixtures in each of these phases. So that's just going to be our Xi and our Yi. Because once we find the Xi and Yi for benzene, we can easily find it for toluene because we're just dealing with a binary mixture. And if we were to have, say, 60% vapor or 60% benzene in the vapor phase, then we would have 40% toluene in the vapor phase. So that'll be easy for us to find. So to begin coming up with our Rashford-Rice equation, let's start with a fairly obvious observation, and that is going to be that the sum of our mole fractions in the vapor phase, Yi, minus the sum of the mole fractions in our liquid phase is going to be equal to 0. So this is a pretty obvious statement. It's just that the total fraction of moles in our vapor phase is going to equal 1, basically, because if we have 40% benzene, 60% toluene in the vapor phase, that's going to equal 1. So it's basically like saying 1 minus 1 equals 0. So we can rewrite this as one summation with yi minus xi equals 0. And then with summations, we need to have a starting value, which will start at 1, which is going to be the more volatile component. And at the top, we'll have n, which is going to be the number of components in the mixture, which in our case, we're only dealing with 2, so that number would be 2. So now we have all of the equations that we need to come up with our Rachford-Rice equation. All right, so let's begin by doing some substitutions. So we want to get one of these components alone. So let's substitute our ki expression for yi. So that would just be ki times xi is equal to yi. So then we can go ahead and plug that in. I'm going to leave the summation symbol off for now. But we'll have ki times xi minus xi. And we can go ahead and factor out those xi's just to make it look a little nicer. We'll have ki minus 1. So we still don't know what xi is. So we need to come up with some way we can substitute in for that. So I'm going to number our equations over here just so they're easier to reference, because we'll be using the first and second equations in our substitutions here. So if we were to look at equation number 2, there is a yi in this equation and an xi. So we can do the same substitution that we did just a minute ago and substitute in our equation for yi. So we would have t zi equals v times ki times xi plus L times our xi. So now we have 3 variables in here that are unknown, with our xi, our v, which is our flow rate of the vapor, and L, which is the flow rate of the liquid. So to lessen this amount of unknowns, we can use equation 1 to make a substitution for L. So we'll get that Tzi equals V Ki Xi plus, that would be T minus V times Xi. Next, what we can do is factor out our Xi. We would have Tzi equals Xi V Ki plus T minus V. Then we can get X alone. So we would be left with Tzi over V Ki plus T minus V. And why don't we go ahead and factor out a V from this denominator here. So we'll have Tzi over V times Ki minus 1 plus T. All right, so the next part that we can do here is pretty clever, actually. We can divide our numerator and denominator by 1 over T. I'm actually going to, now wait. So we'll have xi is equal to zi over d over t times ki minus 1 and plus 1. So now we have xi alone. We can make a substitution for this xi up here for our summation equation, and that's going to give us our final Rashford-Rice equation. So I'm going to go ahead and clean some of this up. We'll just move it over here. So our final Rashford-Rice equation is going to be our summation from 1 to n. We'll have zi times ki minus 1 divided by d over t ki minus 1 plus 1. So that's going to be our final Rashford-Rice equation. And you can see here, now our only unknown is going to be our V, which is the flow rate of the vapor coming out of our system over here. So we are then going to use, once we find V, we can then use that value to calculate our L, which is the liquid coming out, the flow rate of the liquid coming out. And then we can use equation 2 to find the components of the vapor phase and liquid phase. In our next video, we are going to actually be solving for these values. And since we are dealing with a binary composition, our n is going to be 2. We can go ahead and do that because we have 2 components in our mixture. So yeah, thanks for watching this video, and look for the next one where we code out this equation so we can compute those values for the flow rate of the volume or the vapor, the flow rate of the liquid, and the mole fractions of the more volatile component in the liquid and vapor phases.